Okay, good afternoon, everyone, and welcome to our Energy Savers QFF webinar. Today we're going to talk about pump and motor efficiency, and we have a special guest, Phil Szabo from Saturn Engineering Group, joining us. Hi, Phil. How are you?
Good, thanks.
That's good. Yeah, thanks for joining us, Phil, and thanks to others for joining us either live or watching it later on YouTube. I'm just going to run through a couple of intros and then I'll just introduce Phil to talk about pump and motor efficiency. So I'll talk really quickly about the Energy Savers program. It's one that's been delivered by the Queensland Farmers Federation in conjunction with our industry members, who are all listed along the bottom of the screen there. It involved a series of energy audits, tariff reviews, and helping farmers to achieve the savings identified in the audits. And I'll also talk briefly about a tariff research project that we'd like to involve a couple of people in. I'll introduce Phil Szabo in a minute from Saturn Engineering Group. Phil did quite a lot of Energy Savers audits for us. He's also separately done energy audits on different types of industries for Ergon Energy as well. And he's also been doing some measurement and verification of some of the energy audits that we've done through Energy Savers, as well as lots of diesel efficiency assessments. So the basic idea of the Energy Savers program was to offer an energy audit to the Australian standard for farms throughout Queensland, and we did 180 of those. And on top of that, we had 130 that we've done in partnership with Ergon previously. So we've now done over 300 farms across Queensland. This program we wanted to help farmers implement, so the government attached a $20,000 implementation rebate to those farmers to implement recommendations from their audit. Then we've gone back, they're hopefully achieving savings, and some of those that have done that, we're going back and doing measurement and verification on those farms, which means we're actually measuring how much of a saving they've achieved and testing how good that is in comparison with what the energy auditor recommended. So we've done about 30 of those. So just in a nutshell, the audits have uncovered a huge amount of savings across the farms. Across those 180 audits that we did, there were 665 recommendations with a potential energy saving across them of 7.5 million kilowatt hours, which is an average of about 40% per farm on those particular areas of the farm that were measured. So that's not 40% of the total farm bill, but just of those particular areas that were. That results in about $2.8 million worth of cost savings and about 6,000 tonnes in emission savings in tonnes of CO2 equivalent. And then we're finding through the measurement verification process and discussion with farmers lots of other benefits as well, such as better yield, some better product consistency. Farmers telling us that they now know exactly how much water they put on paddocks because they've got the pressure sensors. And then I just want to add that this program is funded by the Queensland Government under the Energy Savers program, and it's been delivered by us, Queensland Farmers Federation, and our member bodies. So I'm just going to go to Phil. Like I said, Phil's been one of the auditors that's worked on a range of different farms for us, various cropping farms.
Alrighty.
Some of those energy audit findings, some of good learnings, audits. Phil, welcome. Just give me a second to do this, but you can.
So has that come up there?
Yes.
Alrighty, thank you, Andrew. As As Andrew said, my name's Phil Szabo. I'm from Saturn Engineering Group, used to be known as Tailored Engineering Solutions and Research. Today we're going to have a look at some pumps and energy. The topics we'll be discussing are energy audits, pump station energy efficiency, benchmarking, the low-hanging fruit from conducting an energy audit or assessment, pump selection, pump curves as we go through the pump selection process, and the age-old question of what do I choose, electric or diesel? So to start off with, we'll look at energy audits. There is an Australian standard, it's 3598 for 2014.2. That's for industrial. There's 3 for commercial and 3 for transport and 1 for commercial. In an energy audit, there are 3 levels. The first level is all about a desktop review. So we have a look at your annual energy bills, whatever that might be, the electricity, diesel, unleaded petroleum, gas if it's used, and we look at the cost, the breakdown of the cost and the consumption. So you can see here that we've got 58% electricity. It's doesn't state whether it's consumption or cost, but if this is consumption, and the cost is much higher than what the actual consumption levels are, then we can look further into those sort of areas. Second level is level 2 site investigation, where we go out on site and we look at all the items that are consuming electricity or diesel or any form of energy, any processes, and then we break it down even further into where it's used. So it could be irrigation, planting, in-crop, harvest, post-harvest, fallow. This is an example from the cotton industry. But for each, it doesn't matter what you grow, there's a certain process that you would follow in growing it, and we can break down that energy consumption. Now, the third level of an energy audit is a detailed investigation into a particular piece of equipment or process. So predominantly, pumps have been known to consume the most amount of energy on farm, and they're often the ones that are down the back paddock and have very little investment in them. So therefore, I specialise in pump assessments. There are other areas that you can look into depending on what the level 2 assessment tells you. So you might put a lot of energy into refrigeration, or in your packing sheds, or whatever the case might be. So they're the areas that you want to try and conduct your level 3 assessment towards. Now here we have a pump station. We've got 2 pumps. There's a large one and a smaller one, and we're going to look at how we work out the pump station efficiency. So the first thing we do is look at the energy in. In this case, we've got 2 electric motors. We can look at the interval data that we can get from the electricity provider or from the electricity meter that's on site. Or we can also have diesel engine driven pumps. Energy out can be in the form of the water flow rate and the total dynamic head. So in this case, you can see, you might be able to see a little bit of equipment. We've got an ultrasonic water flow meter on the suction pipe. And then we've got 2 pressure gauges, one on the inlet of the pump, one on the outlet of the pump, and that will give us our total dynamic head. For those of you that are a little more astute, you might notice that the discharge pressure gauge is up at the top of the bend. It would be better to have it down right at the outlet of the pump, because then that takes into account the losses and the elevation of the bend in the pipe there. To save having to drill a hole though, I put it into an existing hole and just did the calculations for that bend and measured the height difference. So once we've got our energy in and our energy out, we can then work out our pump station efficiency. And that's as simple as putting the energy out divided by the energy in, and it gives us a percentage. And that can range anywhere from as low as 30, 40%, even lower, to 60, 70, 80% depending on how good the pump station is. On average, we see it around the 50% mark, 50 to 60% mark. This figure, the pump station efficiency, doesn't take into account the motor efficiency or separate the motor efficiency, the drivetrain efficiency, or the pump efficiency. It's looking at all the energy that goes in and what comes out at the other end. All right, we're going to look at some benchmarking figures that can be used from year to year. Benchmarking is the quantity of energy consumed against a unit of measure for production. So if we look at an example, we might be growing wheat and we might produce X amount of tons of wheat, and we consume a certain amount of energy to produce that wheat. So we can divide one into the other and we get a benchmark, the number of kilowatt hours consumed to produce a ton of wheat. Another way to look at it is litres of diesel per tonne of whatever you could be growing, in this case barley. And we look at some more specific cases for pumps. So as a grower, you'd predominantly want to see your kilowatt hours per megalitre. It's an easy number to work out. You get either your monthly or quarterly electricity bills, so you know what your total consumption is for that period. And then you have your water bill as well, that you can use for a set period, whether that might be monthly, quarterly, or annually. You can divide the two numbers together, and that gives you a figure for how many kilowatt hours per megalitre you consume. Now that's great as for the grower. As the auditor, I'm more interested in kilowatt hours or litres of diesel per megalitre per metre head. Now this gives you like the efficiency of the pump station. And generally for electric pumps, we're aiming for around 3.8 kilowatt hours per megalitre per metre head, or for diesel is around 0.8 of a litre per megalitre per metre head. And we'll see some of those numbers towards the end of this presentation as we go through the pump selection and electric versus diesel examples. So as I just said, these figures can be used to monitor your energy usage throughout the year and year on year, to see when you may be required to do some maintenance or upgrades or replace the pump station itself. So the low-hanging fruit. For 10 years now, I've been crying this mantra: if you measure it, you can manage it. Energy assessments provide an energy management plan. So you can look at, you can figure out how much you can grow this year, depending on the budget that you have for buying the various ingredients required: diesel, fertilizer, seeds, whatever it might be. So when it comes to your energy plan, you might say, right, I need to grow 100 hectares of cotton and I need 6 megalitres of water to do it. You look at your benchmark figure of consuming so many litres of diesel per megalitre, and then you can work out from that how much diesel you're going to need for that season. Or you can go the other way around and say, I've only got a budget of $100,000 for diesel this year. How much can I grow with that? And then you take into consideration all the other elements, such as fertilizer and seed and so on. Electricity tariff selection. So an energy audit or an assessment will help you select the right tariff. You can look at when, like for example, you can look at when you're irrigating. Can you irrigate of an evening or of a night time and use the off-peak rate? Is it worthwhile installing a solar system and maybe getting onto a peak demand tariff where you can reduce your peak demand and take advantage of the lower consumption rate? So energy assessments will provide that sort of information for you. System performance. So as we just saw, you get your benchmark figures from an energy assessment. You can see how it's performing. So if you've got a 5-year-old pump, you can see how much it's declined in the past 5 years, or 10 years, or 20 years, however long it's been installed for, and make decisions on when it needs to be replaced. Can you get another year or 2 or 5 out of it before it needs to be replaced, or before you need to pull anything up? Are there any problems with the pump? So is the electric motor running fine? Is the diesel engine running okay? Is the pump doing what it needs to do? Also, you'll get the figures, as we just mentioned, the peak efficiency. You'll see on the pump curve, which we'll talk about in a moment, what your peak efficiency is, how far you are from it, if what you can change to get to your peak efficiency, to try and improve your energy efficiency. And then maximum water flow rate is another one that we can determine from an energy assessment. So you may have the pump set at a certain RPM or a certain frequency, and it will deliver so much water. But if you turn that frequency up or increase the RPM, at what point is the maximum water flow rate going to occur? So an energy assessment does give you that information. All right, moving on to pump selection. First of all, we need to determine what the pump task is. And to do that, this is generally done in an irrigation design aspect, but the first thing that we need to know is how much water do we require. So we can look at the irrigation system that we have. Might be a lateral move where we're trying to irrigate 60 hectares and we want 20 mil of water across the top of that, or whatever it might be, 300 mil for the season. So we can work out how much water we need to apply, and we get a flow rate from that. The second one is the associated pressures. So we'll talk a little bit more about the pressures and where we get them from. But when we combine these two elements, we're given what's known as a duty point. And if you've got multiple fields that need to be irrigated from the one pump, you might have multiple duty points across your pump curve. So you need to try and fit them onto the one pump, or you may need to get a second pump if you're for certain fields to increase the pressure and the flow rate depending on what's required. So now we're going to have a look at the pressure required and how we determine that pressure. It's known as total dynamic head, and it's measured in meters head. It consists of the following components: the static elevation. As you can see in the diagram here, we've got a relative level going from 70 meters at the suction side, going up to 100 meters on the discharge side. So the difference between that is 30 meters, which gives us our static elevation between the two water levels. Next is the irrigation system requirement. So on the end, if we've got a lateral move, that lateral will have a required pressure at the tower, and generally around 2 bar, and that means that there will be enough pressure to get the correct atomization through each of the irrigation nozzles attached to the lateral move. So we need to include that in our total dynamic head. Friction losses. So you can see here in this diagram, we've got a whole heap of pipes and elbows and bends and valves and the like. All of those have an associated friction loss in it that needs to be determined and then added together, and that gives us the summation of all those components and give us the friction losses when working out the total dynamic head. Now the next two, while they're not very high, they are still important and need to be considered. They are velocity head, which is generally measured at the pump inlet and outlet. It's just an equation that uses the velocity of the water, and the vapor pressure. That takes into account the temperature of the water and the atmospheric pressure on the day. Now, these two numbers are generally very low. For example, the vapor pressure at 20 degrees at sea level is around 0.25 of a meter, 250 mil. So when you're looking at a system that has 50 meters worth of total dynamic head, it doesn't account for a lot. But when you look at a system that only has 5 meters, it can, in that case, it does account for a lot. Same with velocity head. That's all dependent on the velocity of the water going through the pipe. So again, it can be low, but it's something that needs to be considered when you have a low total dynamic head. So moving on, Back to the original question, we need to determine the pump task, so the water flow rate and associated pressure. And after going through that, I've put an example together and I've come up with a water flow rate of 75 litres per second and a total dynamic head of 51.8 metres. So with this information, we need to move on and start looking at pump curves. So I've narrowed our selection down. This is a Southern Cross pump. We're looking at trying to plot the duty point of 75 litres a second with 51.8 metres. So if you look down on the horizontal axis, we have water flow rate. In this case, it's in litres per second and cubic metres per hour. Up the top, we've also got water flow rate, and it's in US gallons per minute, and there's another gallon litre. What's that? Gallons per minute again. Imperial gallons per minute, sorry. So we plot our water flow rate, which is 75 litres a second. Now, our total dynamic head is on the vertical axis in a pump curve. Oh, sorry. On the vertical axis in a pump curve. And on the left-hand side here, we start at 0, we work up 10, 20, 30, 40 metres and so on. On the right-hand side, it gives us total dynamic head in feet. So we plot that point that we've just been given, 75 litres a second, 51.8 metres, and it lands here on the pump curve. But there's a lot of lines on here, and it can be quite confusing to look at. But we'll break this down step by step. So if we look over on the left-hand side, we've got some numbers. This refers to the pump speed. So these curves can be given to us in either a variable speed curve or a variable diameter. In this case, it's a fixed diameter of 342 mil and a variable speed. So we start off with 1800 at the top. That's the 1800 RPM curve. We move down to the 1600 RPM curve and so on to the 14, 12 and 1000 RPM curve. So in this case, we're looking at around 1710 RPM for this particular duty point. Now, what that tells me is that we're not going to be able to use a fixed shaft. We're going to either need a gearbox or a drivetrain or some form of drivetrain belts to match the speed between either an electric motor or for an electric motor or a diesel engine. Now we'll cover that in a little more detail in a moment. The next thing that we want to look at is our efficiencies. So we've got a whole range of efficiency lines along the top here, starting at 40%, 50%, 60, and so on, all the way up to 84% efficiency in between those 2 points. And then we move across and it goes down to 60, sorry, what's that? 84, 83, 80, and 75 in the pump efficiency range. You can see the 84%, how it loops around with the lines. Same with the 83, comes down, and the 80% efficiency. So in this case, we're looking at around 84% pump efficiency. Now, we need to know how much power is required because we're going to want to choose an electric motor or a diesel engine in a moment. And that can be done through these set of lines on the right-hand side. They're dashed lines, even harder to see. But we start off here at 55 kilowatts and we go down to the next one at 45 kilowatts. And then we obviously range between. So in the middle of those two lines, we'll have 50 kilowatts will be our requirement. In our case, for our duty point, that's right on 45 kilowatts. So that means that the pump shaft requires 45 kilowatts with 84% efficiency. Another parameter that we have on this curve is what they call the net positive suction head required. So if you go back to the diagram that we had earlier, on this side of the pump, this is our suction side. This produces a negative pressure, and there's only so much that we can lift. The NPSHR gives us those figures, and we need to calculate what the total dynamic head on the suction side is to make sure that it meets the requirements. There's a lot more involved in that. That's a very quick explanation for it, but those curves are also produced. They're also dashed lines, but they're produced on this pump curve.
Excuse me, Phil.
Yes.
We just can't see your cursor. I think you're
Oh, really?
With your cursor, yeah. So maybe if you could just describe as you go in a little bit more detail, please.
How's that? Is that cursor up there now?
No, I can't see it.
All right. So down the bottom of the curve, near the 1000 RPM line, is where we have the net positive suction head required. You can see we've got 2 meters, 1.6, 1, 1, 1.6, 2, and 2.5, and then it goes up on the right-hand side of the curve, continues at 4 meters, 4.5, up to 6 meters. That pretty much covers the pump curves, short of going back and doing it all again. We might just move on from there. So now we're going to look at what we install, whether it's an electric motor or a diesel engine. As you can see, we've got an example of each there. So what we need to consider are the capital expenditure for each. If you want to convert from diesel to electric or electric to diesel, these are important. You can look at like the costing to install a pole is around $10,000 a pole. Transformers need to be of adequate size to meet the current load plus the load of the pump that you're putting on. So you could be looking at increasing the capacity of the transformer. And that can start at around $30,000, $40,000, $50,000. Diesel engines, depending on the size that you want, you could be looking at $20,000 to $50,000. Now we need to look at our annual operating hours. Now I'll have a table at the end of this that will highlight why we need to take this into consideration, and that it can be the difference between choosing a diesel engine and an electric engine as well, electric motor. Any potential for renewable energy. So I said earlier that we might be able to use some solar for a tariff selection to get onto a demand tariff to reduce our peak demand. But it gives us the benefit of a lower consumption rate. And then operating cost for each energy source as well. What's the you get through the selection? We know from the pump curve that we've just looked at that the shaft output required is 45 kilowatts. We know that going through the motor speeds to have a direct drive, we need either 980, 1440 RPM or 2800 RPM. We require for this example 1710, so we don't meet any of those requirements or speeds for a motor, which means that we need to install some form of drivetrain or speed reduction. In this case, we're using a drive belt or belts, and we need to account for 10% additional energy to drive those belts. So that takes our power requirement from 45 kilowatts to 49.9. Now let's have a look at a diesel engine. So we require, call it 50 kilowatts to keep it simple, at 710 RPM. If we look over at this engine curve, we can see under the power output in the middle table, you look at 1700 RPM, we require 69 kilowatts. So let's say for argument's sake at 710, it's about 70 kilowatts. So that means we only require 50. It produces 70. That meets our requirement. So this engine is suitable. Now we need it at 1710 RPM. So if we look at the bottom table, we can find out what our specific fuel consumption is. And at 1710, it's a touch over 217 grams per kilowatt hour. Now I've done the maths for all of that, and that comes out at 12.7 litres of diesel per hour of operation. So now we know the fuel burn rate for a diesel engine. We need to figure out what it is for an electric motor. So we still need the drivetrain, we still need the belts, so we still need to add on that 10% for belt losses. So we still require the 50 kilowatts. We're going to install an electric motor that has that's 94% efficient, and that takes our energy consumption or electricity consumption to 52.7 kilowatts. So moving on from there, we're going to put some costs for each section or for each energy source. For diesel, we're going to have an assumed cost of $1.10 a litre. Seems a little bit cheap at the moment, but when you take out GST and the excise, it does come down a little bit. The benchmark figure that we received doing all those calculations was about 0.9 of a litre or 0.91 of a litre per megalitre per metre head. And we're looking for, remember the target is around 0.8. So we're not going to get that every time. And in this case, we haven't achieved it because we've got the 10% losses by including the belts. So that does, each little bit of inefficiency does increase the cost. In this case, we're looking at $1 per megalitre per metre head when we do the maths. Now let's have a look at an electric motor. So looking at tariff 20, which is 24.8 cents per kilowatt hour, the cost comes out at 93.4 cents per megalitre per metre head. So it is a touch cheaper, to almost 7% cheaper to run it off the grid, off electricity, than it is to operate a diesel engine. However, there's always more. These numbers don't take into account the maintenance of diesel engines or the electricity supply charge or peak demand for that matter. So let's have a look at some maintenance and supply costs. A diesel engine needs to be serviced every 500 to 1,000 hours approximately and can cost $750 to $1,000 per service. The electricity supply for tariff 20 is $485.94 per annum. That's for the current cost. So now if we look at a comparison table between them all, between the diesel and electricity, based on operating hours, we can see that if we're just using the pump occasionally, 100 hours a year, that the diesel costs are just under $1,400. Whereas electricity, it's just over $1,300. So it's $1,307 compared to $1,397. But then if we take into account, if we install a solar system as well, and we can get on a tariff 24 and try and manage our peak demand as best as possible to negate it, then the cost comes down to $884. Now, as we increase our hours of operation, you can see that the numbers, that the cost significantly reduces as we get into, or not, sorry, I shouldn't say significantly, but it reduces as we get into more and more consumption with electricity. And if we can manage that further with some solar, then we get that significant reduction in cost. So this is where your management plan comes into place with solar and seeing how you can irrigate or when you can irrigate to try and offset these costs. Now, looking at tariff 24 with solar, you're thinking, well, I'm not going to irrigate over night time. Why did I install the solar? That is true, but that just gives you a greater window of when you can operate now, because before you're paying a higher rate in tariff 20, whereas now you can irrigate during the day and the night for tariff 24 as the peak demand is between 10 a.m. and 8 p.m. on weekdays. So you can see conducting these sort of energy assessments can add valuable information as to when and how you're going to implement any sort of improvements or upgrades to your pumping stations. That is all that I have. If you require any further information or would like any sort of energy assessments, then my details are as follows. Thank you very much, Andrew. I'll hand it back to you.
Thanks very much, Phil. That was really interesting, and it is interesting you did that tariff comparison too, because I'll come back to that a bit later and ask you a couple of questions about that. For the people online, there's a little chat function there if you'd like to type any questions into that. I'll even see if I can unmute you if you just indicate in there that you're keen to ask Phil any questions. But Phil, you were talking about a worked example of an energy audit. We do have a little bit of time if you thought it might be valuable to go through that and just step through the process.
Yep, I'll just bring it up. I'll just unshare this, the current page. I was here a second ago, sorry.
So I might just ask another question while you bring that up. So what, I mean, you've obviously done quite a lot of energy audits of diesel and electric systems, and particularly in energy savers, you looked at a lot of electric systems because that was the program, was about electricity savings. What were some of the most common things that you found across the audits that you did as far as potential efficiencies?
Electricity tariffs were a big one. So making sure that you're on the right tariff, just making sure that the pump station was set up correctly as well. So understanding where your energy is going. Suction side. So we touched a little bit on the suction side. A lot of suction side. A lot of the pipes would be too small and consume too much energy. Pipe diameters would be too small, so your friction losses are quite high. You're not getting enough water out at the end of your center pivot or lateral move. Electric motors were failing, or their performance was declining. Yeah, and I'm sure there were others, but they're the ones that off the top of my head. So I've got this report here. I'll just try and share it. It's an example report from one of the audits that we conducted. That doesn't want to come up, sorry. It's not in the list that I can share from. Here it is. All right, so here's an example report. Can you see that, Andrew? So I've got the energy performance analysis. Has that come up? Yep. So what we've done here, we've looked at 3 different pumps, and all 3 pumps are responsible for the same task. They want to irrigate through a travelling gun. One pump is on a creek. We've got a mixed flow pump on a creek, and we've got 2 bore pumps, a small one and a big one. And they can all operate together depending on where the water is. They can all operate together, or they can operate independently, except for the small bore pump. It requires one of the other pumps to supply sufficient water for the travelling gun. So when I arrived, we I had a look at the management plan, the current management plan on how the pump works with the varying sizes in the nozzles. You can see here that we've got 40.5 hertz, 43 hertz, 47 hertz, and that was with just the single Davy pump operating, the mixed flow pump. Then we've got the Davy pump operating simultaneously with a bore pump, Luara bore pump, and we've got the 28mm nozzle and a pump speed or a pump frequency for the Davy pump of 42 hertz. And again for the Davy pump and the Grundfos pump. So both of those had VSDs, variable speed drives on them, and we had two sets of frequencies. So the Davy pump would operate at 40 hertz, the Grundfos pump at 42 hertz with a 28mm nozzle, and then the Grundfos pump and the smaller bore pump. We've got two frequencies for the Grundfos bore pump. The Luara bore pump was a single speed. So it was set up to operate at 130 PSI on the Luara bore pump gauge. That's how the grower operates it. He turns it on, sets the gate valve until he gets 130 PSI, and we're done. It's good to go. So from the assessment, from the energy audit that we've conducted, we can see here, these are the results operating the various duty points with the 24, 28 and 30mm nozzles. We can see our combined efficiencies are 70, 72 and 71%. Pump efficiency, 76, 78, 77%. Now we're going to look at, we looked at the Davy pump with the small bore pump. So we set the small bore pump to 130 PSI. Our combined efficiency has dropped to 60%, 50%. Pump efficiency for the Davy pump was 65%. So it's a big drop going from our peak at 78 down to 65. The Luara pump was 55% efficiency. Looking at the Grundfos with the Davy pump, we've got almost 70% for the Davy pump. So again, we've still got that drop in efficiency by adding in the second pump. It's changed the duty point for the pump, moved it across. So if we look at the pump curve down the bottom, we're only able to fit the one duty point in this case for the Davy pump. It didn't fit for the Luara and the Grundfos pump, but we can see here in the Grundfos, for the Grundfos pump, how on the pump curve, how the efficiency changes for each duty point. So if you follow each of the green, red, and purple lines, you can see where the efficiencies are, how the efficiencies are changing with each duty point. All right, so we'll scroll back up, keep going through so we can get to the results of this energy audit. Now, in the results, we found that the creek pump, the Davy pump, was performing really well. Can't complain about it at all. Its cost. So here we're consuming 3.86 kilowatt hours per megalitre per metre head, 3.78, 3.83. Our target is 3.8. So extremely happy with those numbers. Not so good when it comes to the in combination with the bore pumps. So what we found, trying to cut this down a little bit because we're going to run out of time, sorry, is that changing the pressure for the small bore pump, adjusting it to 100 PSI, improved the efficiency of the pump. So we've gone from what was a 55% to 57%. The usage has gone from 5.46 kilowatt hours per megalitre per metre head down to 4.78 megalitres per kilowatt hours per megalitre per metre head. Our consumption has reduced from 585.6 kilowatt hours per megalitre down to 425 kilowatt hours per megalitre. So there is a big savings there. And I'll skip to the last point here, that there seemed to be some issues with the Grundfos pump, but we couldn't figure out. The grower didn't know whether it was the pump, the motor, or something in between. Why there was an issue? So from the assessment, we determined that the pump, there was nothing wrong with the pump. It was doing what it needed to do. It was, the duty point was on the curve where it needed to be, but we found that the electric motor was consuming 7.1% more electricity than it needed to. And it turned out that there were faults inside that motor, because the grower pulled it out and he found faults inside the motor. The motor was replaced and put back down the hole. So there's some of the, in a nutshell, and a very quick explanation of an energy audit, the results from an energy audit, the numbers that we get from it, and the benefits of conducting the audit. Thank you, Andrew.
Thank you, Phil. I've just had a question put to us. Can you give a bit of an indication of the cost savings available for using variable speed drives? Perhaps there might have been a couple of recommendations from audits that you did.
Yep. So for a VSD, installing a VSD, if we look at this Loara pump curve, so if we were to put a VSD on it, we could improve or change the speed of the pump, so we could move the vertical red line across so it's meeting the efficiency or the peak efficiency for that particular pump. So we're going from up like 55% efficiency up to 57% in this case. So there can be significant savings by having a VSD to adjust your operating parameters. Difficult to put a number on it because it all comes down to operating hours again, and where the pump is operating in the number of duty points that you have. So looking at the Grundfos pump, you can see the change that we have here from the 3 duty points. If that didn't have a VSD on it, would be stuck with the 1 point. And as you can see, the green duty point is the efficiency is quite low compared to the other 2, as it due to the increase in speed. So to quantify an actual cost saving is difficult. Depends on the operating hours generally, but you could be looking at 10, 15, 20% operating cost reduction. Back to you, Andrew.
Thanks, Phil. Yeah, I hope that answers the question. I'm just going to share my screen for a second and show our case study website, because that's got some actual examples of where some variable speed drives have realised some savings for farmers. So I'm just showing our web page live at the moment, the QFF case studies. So it's qff.org.au. Look for the Energy Savers program and go to case studies. And in our case studies search function up here, you can search by industry sector, by location, pump type, irrigation type, and everything. But also you go to this technology tab here, find variable speed control there, and then there's a group of case studies there that all have variable speed drive savings in there in the case study. You can see savings there ranging from 39%, 11% to 40% and greater, and that includes a range of other things as well as variable speed drives. But there's an option there for you to have a look at and see some other savings as well from variable speed drives. I'll just pick up where I left off before. I just wanted to finish with one other little case study and then just a bit of information about some tariff research we're doing, which is follows on from how Phil finished his presentation nicely. So this case study is a horticulture case study. This one's been measured and verified, which means The auditor has gone back out after the implementation of audit findings and measured the actual findings. Just on that screen there, you can see a bit of a summary of the site. They already had 30 kilowatts of solar on the roof. You can see the site energy balance, which Phil highlighted in his presentation as an essential part of the audit process. And in this one here, the big green wedge there is irrigation, and the big orange one are the cold rooms. So hence the focus in this case study on irrigation and refrigeration. There were some really good easy wins in there, and by that I mean fairly low cost wins in the refrigeration side, like cleaning and dusting those coils, replacing the leaky roof and some door seals. There's some more expensive ones, like using putting a new roof. There's a cold room there exposed to daytime sun all day, so they put a cold roof over that cold room, and then favouring their efficient cold rooms, so that the energy audit allowed them to rank their cold rooms in terms of efficiency, and it means that when they're not operating at full capacity, they can favour more irrigation, a few leaks and blockages, and a pump upgrade, and then some LED lighting which they've installed throughout the building in areas where they do use lighting. So they've gone ahead and implemented all of those recommendations. And interestingly, that's the old pump there. So this pump, going back to that question, did have a variable speed drive, but when the auditor mentioned it, when the auditor measured it, they couldn't get the flow rates to reconcile with the pump curve. So they did some more detailed investigation and found that the impeller had been adjusted, so it wasn't actually performing as it should do on the pump curve. So the auditor recommended upgrading the pump, keeping the VSD, and that's resulted in an irrigation efficiency improvement from 4.36 megalitres per metre, kilowatt hours per megalitre per metre head to 3 kilowatt hours per megalitre per metre head. Now that's a little bit lower than Phil's target range, and I just looked that up after Phil mentioned that, and a couple of those blocks are down below the pump level, so we've got a bit of gravity helping out those ones too, but nonetheless, it's about a 30% saving. The farmer's also reporting that they're getting some increased production because they've got better water flow, more consistent water flow. And one of the other benefits there of having that roof over the cold room is they're better protected from storms and weather. There's a little QR code there if you're watching and you want to jump straight to that on your phone, that case study. I will just show you that case study on our website so you can put it in your own time. And that's it there. So that's what the case studies look like when you select them off that case study website. It gives you a summary of that it's implemented, the energy savings, the emissions savings and cost savings, and a bit of a summary of some of the technologies that have been applied there as well. I'll just go back to my presentation. I did just want to invite you to participate in a bit of research we're doing on tariffs. One of the issues that we've identified through the program and just through other activities like a microgrid project we're working on is just the complexity of energy tariffs. And this that was sort of highlighted by the change of tariff and the inclusion of some of the obsolete tariffs on the 1st of July. And so some of the audits have found switching tariffs have been beneficial. And there's a good case study on our website of Mariba Banana Farm that saved over $20,000. What we want to do is, working with the University of Queensland, understand how farmers choose tariffs their operations, whether that be choosing between the various ergon tariffs they have available, or if they're not in the ergon area, so if they're in New South Wales or the Energex area, for example, how they look at the different retailers and different tariff offerings they've got available. what we want to do is use that information to inform the design of better tariffs. So we'll use that as UQ and QFF to help design better tariffs, and also help design tools to help farmers choose tariffs. We're looking for 70 farms just to participate in this program, and what it involves is a quick survey over the phone. That's moved slide, Phil, hasn't it?
Say again, sorry?
That's moved slide, it's moved on. Yeah, so what we'll do is we want to do a quick phone or Zoom interview for around 30 minutes. We'll ask you questions about what tariff you're on, what retailer, if you've switched recently, and how you went about doing that, what you took into consideration. We do have an extra little benefit of a $40 gift card for people that give up their time to participate. And if you're interested, please scan that QR code off your screen now, or go to that SurveyMonkey link, and there's just a couple of quick questions. Just in wrapping up, a couple of other case study and information websites there for you on the QFF website to give you a bit more information. Otherwise, please contact us on that Energy Savers at QFF email address there, and we'll answer any questions that you have about energy efficiency, renewable energy on the farm, and tariffs, or to put you in touch with Phil Szabo. So Phil, thank you again for your presentation this afternoon.
No worries. Thank you for having me.
Is there anything else you wanted to add?
No, I think that covers it all for today.
Can I just ask you a really quick question? I saw you present at an energy efficiency forum for cotton farmers out in central Queensland a couple of years ago. You told a story about a farmer that was irrigating with 2 diesels, and he was working on the sound of the diesels, thinking he had the most efficient operating point based on what sounded like to be the most comfortable RPM for the engines.
Yep.
I think you said, so there were basically 2 engines operating low revs to deliver the water to the farm, and you did an assessment of both pumps and found something different in there.
Yes. Yeah, just because it's the engine can run at 2200 or 1800 RPM doesn't mean that that's the best speed for the pump. I found that the pumps were actually cavitating at those higher speeds. So if we knock the speed back to 1500 RPM in this case, we were getting the same amount of water, but rather than consuming 45 litres an hour, we were consuming 25 litres of diesel an hour to get the same amount of water. So going faster or having a bigger engine does not necessarily mean that you're going to get more water.
Excellent. Okay. Well, that's a great note to finish on. I'm just going to leave that screen up for the last couple of minutes. But Phil, I really appreciate your experience. Thanks for all your work on all the audits and M&Vs you've done the program. People that are watching, if you'd like us to put you in touch with Phil for some energy assessments on pumps on farm, please get in touch with us at that email address, and we'd also love you to participate in that tariff survey. So thank you very much, everyone, for joining us today, and look forward to being in touch with you in the future. Thanks very much.
Thank you.
Thanks, Phil.